Hello, I'm Ethan. The paper I'm going to talk about is research on prediction of photovoltaic power generation probability interval based on Gaussian mixture model. The transition to renewable energy, particularly solar energy, is critical for global economic development and energy transformation. Photovoltaic power generation stands out as an efficient method for harnessing solar energy. However, its randomness and volatility present challenges for maintaining stable power grid operations, highlighting the importance of accurate PV power prediction. Accurate forecasts help mitigate the adverse effects of output fluctuations, which can otherwise destabilize the power grid. The paper proposed a novel approach using a Gaussian mixture model to improve the prediction of PV power output. This method involves clustering prediction errors based on weather conditions to better fit the error distribution. By leveraging GMM, the accuracy and applicability of PV power interval predictions are significantly enhanced. GMM provides a more accurate representation of the prediction error distribution, accounting for its multi-peak nature. Clustering errors based on weather types allows for more tailored and precise predictions. The paper identifies that traditional methods for predicting PV power generation often rely on single distribution models, such as normal distribution, which fail to accurately represent the multi-peak nature of peak prediction errors in varying weather conditions. It highlights that the normal distribution is only effective under specific conditions, such as sunny weather, while in other scenarios, its fitting performance is insufficient. The research emphasized the need for a more robust approach that can accommodate the variability in weather and improve the accuracy of prediction intervals for PV power generation. To address these issues, the paper proposed using a Gaussian mixture model to better fit the distribution of prediction errors, thereby enhancing the reliability of PV power forecast. The paper employs the K-means algorithm to categorize historical PV power generation data based on different weather conditions. This helps in analyzing the prediction errors more effectively by grouping similar data points together. The Gaussian mixture model is utilized to fit the prediction errors obtained from the K-mean clustering. This model is particularly effective in capturing the multi-peak distribution of the prediction errors, which single distribution models struggle to represent accurately. The EM algorithm is used to estimate the parameters of the Gaussian mixture model. This iterative process helps in converging to a local optimal solution for the model parameters, enhancing the accuracy of the predictions. The paper assesses the fitting accuracy of different models using the determination coefficient R². This statistical measure helps in comparing how well the predicted values align with the actual data, with values closer to 1 indicating better fitting. The paper predicts a probability interval of PV power generation by calculating confidence intervals at specific confidence levels, providing a range within which the actual power generation is likely to fall. The dataset used in this research includes actual PV output data collected from June 2018 to June 2019. This data is complemented by meteorological information such as temperature, humidity, and radiance, sourced from the internal meteorological system of the PV power station. The time resolution of the dataset is 15 minutes, allowing for detailed analysis of the PV output and its influencing factors. To ensure the authenticity and accuracy of the research results, the data underwent a screening and cleaning process. This involved identifying and revising any abnormal values, such as negative measures outputs, which were corrected to 0. The dataset was further processed by normalizing the PV output and prediction errors, and classifying weather conditions into 3 categories: sunny, cloudy, and rainy, labeled as A, B, and C respectively. The research specifically utilized data from a PV power station located in Central China as a statistical sample to verify the effectiveness of the proposed prediction method. So in this section, several typical single distribution models and a third-order Gaussian mixture model are used to compare the fitting results of the prediction errors classified according to weather conditions. These figures show the results obtained by fitting the prediction errors by using normal distribution, logistic distribution, t-distribution, and GMM in all kinds of prediction error weather. It can be seen from the chart that only in Class A weather, the prediction error is more consistent with the normal distribution, while in other cases, the fitting effect of the normal distribution is poor, which is not enough for multi-peak and peak fitting. The tail fitting effect of 2 locations is better than that of normal distribution. The logistic distribution fits the spike well. However, there are still some shortage fitting of the multi-peak phenomenon of the error distribution by these 3 distributions. Compared with other single distributions, GMM has a better fitting effect on the multi-peak and the symmetry of error distribution, and is better than other single distributions. Combined with the pre-evaluation index of goodness of fit in table, we can see that in different types of error distribution, the MAE and RMSE of normal distribution, t-distribution, logistic distribution, and GMM show a decreasing trend from front to back, while R-squared shows a gradual increasing trend from the above results. It is easy to know that the fitting effect of GMM is better than that of the other 3 models, especially when the error distribution of Figure 3 and Figure 4 shows above obviously multi-peak and asymmetry the RMSE of GMM4 decreases by 54% and 31% respectively, compared with the logistic distribution with the best effect in a single distribution. To sum up, the GMM4 proposed in this paper is more accurate and flexible than other distribution models in fitting PV power prediction error. And the more complex the error distribution is, the more obvious its advantage is compared with the single distribution model.